I hate the bell. I hate the sound of it. Yeah, I can hear my voice. Everything I'm saying right now. I can hear you guys if you're loud enough. Be loud. Be bold.
Hello.
There it is. So when you watch the video today, you're going to hear Sydney saying, hello. Yeah. All right, here we go. We're going to talk about a type 1 problem. This is the one we did yesterday, right at the very beginning. So it is the same kind of thing. I just want to practice it real quick. And I want to be very clear that I'm going to try and solve these the exact same way every single time so that you guys can see that this is kind of a foundation. If you work the problem in this way, you will always get towards the answer. We're just going to have an object that's at the top of a flat-roofed building. So we'll say this is like 10 meters tall. And it has a velocity of, let's go with 5 meters per second. And it's traveling horizontally at the top of this building. And we want to find where the object is going to land on the ground. So we're expecting the object is going to have kind of a path to the ground that looks like that. We are looking for what we call the range of the projectile, where it's going to land or where it's going to strike the ground. Now, there are other things you could be asked to do in these problems. I'm just looking at the basics of the problem right now. So let's start with organization. As I said to you before, I think it's best that you find a way to organize the information that's going to be presented. And the information that's going to be presented is always going to need to be split up into a vertical side and a horizontal side. With projectiles, the acceleration acts only in the vertical direction. So because of that, we need to isolate the variables that are in the vertical direction. So in the vertical direction, I have all of the Galilean motion variables. There's going to be a change in height. There's going to be an initial velocity, a final velocity, the acceleration, which is very likely in these problems to be gravity, and then how long it takes to fall to the ground. This is all talking about just this part of the trip, the part of the trip where the object is making its way to the ground. At the same time that it's making its way to the ground, of course, it's moving sideways. It's going on this trip here. But in the sideways direction, there's a horizontal displacement, which we call the range. There's a horizontal velocity, but that's constant. It's not going to change. So whatever it starts with will be its horizontal velocity just before it hits the ground. Now, that little piece of information I would really hold on to. It's one of the more frequently asked questions on tests about projectiles. Is about recognizing that no matter where we're looking at the object, even if it's just before it hits the ground, it is going to have the same horizontal velocity all the way down. That never changes. So if I ask what its horizontal velocity is just before it reaches the ground, it's 5 meters per second. Because in this case, that's the horizontal speed it left the building with. Now, its vertical velocity is always changing. It's getting bigger and bigger and bigger and bigger. Because that's accelerating. So I'm going to go ahead and fill up my chart with all the given information. But the horizontal velocity is 5 meters per second. It rolled off the building, which gives me a good 0 to put in there. Whenever I can put a 0 in, that helps. That lunch is good today. And let's see, it's going to fall 10 meters. And will be accelerated downward by gravity 10 meters per second squared. None of that is on the tape, so nothing about talking or my wife or anything. So if you listen back, you're just going to hear it stop, no screaming, and then it start again with, stupid physics. There, so I'm going to put the negative sign there and there because it's going downwards. So you guys see that? I chose up to be positive. You understand that we always choose up to be positive. The one thing you want to be very, very careful about, in fact, this is worth writing a note in your notes about. Don't ever start saying to me that g is negative 10. G represents the acceleration of gravity. Its value is 10, and it's directed downwards. Don't make the assumption it's negative. We're going to be using g a lot in here because your weight is based on the acceleration of gravity. Because of that, we use g for that. But it's not negative. Your weight isn't negative. You're pulled downwards. So I don't want to get complacent about this, and if I have to convince you of it, I'm going to start making up negative just to make sure that we mix it up a little bit, okay? I want you to understand that it's just direction. All right, now, to find the range, we need to figure out how long the projectile is in the air so that we can use that to figure out how far sideways it goes. This problem is about finding the time. So we have all the information we need to find the time. It comes down to, and it will almost always come down to looking at this relationship to figure out how long the object is in the air. Now, the first thing I will point out is that having a zero is going to make this relationship easier to use. That should be one thing you will notice as they get more difficult. When you don't have the zero, it's more difficult to do. If we look at this, this is going to be negative 10 equals 1/2 times negative 10 t squared plus 0t. Now you understand, back to where I was, you do notice that if this weren't zero, all of a sudden this would be a lot harder. Well, think about it. If this was launched at an angle, that would no longer be zero, right? So that's what we're going to progress to, but understand that it doesn't change what we do here. It does make this part of the math harder. Does it make the physics any different? No. It does make it a more difficult math problem. But that's the hard part about physics sometimes, is that you might know all the physics, but can't do the math. And we're trying to make this not always about the math. But at some point or another, the math is a part of what we do for the physics, and that's why it gets hard. This problem itself, though, not so bad. With the zero there, finding time is really, really straightforward. So I'm going to have 10 equals 5t squared. And so t is going to be equal the square root of 2, or 1.4 seconds.
Would it be negative?
No, I cancel the negatives out. Right, there's negative on both sides. So I just cancel the negative. Is that good? We cool to go? Yes, ma'am.
I know in calc we have to round to the 3 points after. What would you prefer?
Specifically in physics, you don't round between steps. So in your calculator right now, the time should be like, go on forever because it's irrational. But physics subscribes to significant figures. So strictly speaking, my answer should be in one significant place because the 5 was the number with the least number of significant places. Strictly speaking. But we don't adhere to it. Meaning you will not be graded on your ability to use significant places. So even on the AP exam.
Okay.
Yeah. So going over here, this is 1.4 seconds. If I want to figure out how long the object's in the air, I'm going to have to multiply my 5 times 1.4. So 5 times 1.4 will give me the range. And that's going to be 7 meters. Not bad? All right. This is pretty straightforward, not too difficult. I want you to understand that there's 3 variations to this problem. And I don't want to do all 3 of them because it's just going to take up too much time. But I want you to go back to looking at this chart and listen to the possibilities. This problem asked for the range, giving you the horizontal velocity, right? If I gave you the range, you could be asked to figure out the horizontal velocity. So think of that one too, because that's one of the ones we're going to actually do for our test. We're going to roll something off the desk. Actually, we're going to shoot something off my desk. We're going to see where it lands on the floor and use that to figure out how fast it was launched from the desk. So the only difference is that instead of giving this number, we'll be given this number. So you just find the velocity instead of the range. The other thing that you can do is you can be given the range and be asked to figure out how high the table was and work backwards that way. That comes up too. Those are the 3 variations: finding the range, being given a range and asked to find the velocity, or being given a range and velocity and asked to figure out how high the table was. The 3 variations to that problem, and that's it. But we have to move on to the problems that I think you asked to see. So let's go on to the ones that are a little more difficult and will involve the trig that we have to have. And the first one I'm going to call this is a type 2 problem. Type 2 problems are characterized by the idea that the object is going to be launched from the ground and land on the ground. So this is a ball that is kicked, a golf ball that is hit. Even throwing a ball back and forth between friends. If the object lands at more or less the same height that it takes off, I classify that as a type 2 problem. And the reason for that is, first, it introduces us to the idea that we're going to have trig. We're going to have a launch angle and a launch velocity, neither of which we can use by themselves. So we're going to have to break this up into components. That's what we were talking about yesterday. However, we do get to introduce a zero in our problem. When we look at our chart and start considering the horizontal and the vertical side, the horizontal side is largely going to be the same kind of stuff. We're going to be looking for a range. But on the vertical side, although there will be an initial velocity and a final velocity, we're still going to have acceleration. The delta y is going to be 0. If the object is landing at the same height that it's taking off, then the displacement's 0. The y displacement 0. The range isn't 0, but the y displacement is 0. If you consider that we're probably going to use the same relationship to figure out the time, you should be able to see that introducing another 0 means I still don't have to use the quadratic formula. So often the type 1 problem and the type 2 problem are the ones that are chosen for the exam because you don't have to solve a quadratic. The simplification exists to make it a little bit easier. So let's go ahead and put numbers to this. Let's assume that we're talking about a golf ball, so it's going to be hit at a relatively speedy 90 meters per second. And it'll be struck at an angle of 30 degrees. Now, trig. Let's take just a moment to discuss trig in case that's going to be an issue for some of you. I'm going to take this little picture and blow it up over here so we can kind of be very careful about our vector portion. So we've got our vector velocity, 90 meters per second, at an angle of 30 degrees. We're going to have to break this up into components. And one of these components is going to be horizontal. There we go. And one of these components is going to be vertical. There we go. So we're going to take this and break it up into components. Is that better? All right. Now, for you guys who are confident, but it's been a while since you've done the trig, components are always at a right angle to each other. This is true for all vectors. We're going to deal with vectors a lot. Component vectors are two vectors that are at right angles to each other that make up a third vector. They do the same thing. I want you to imagine, if you would for just a minute, that you're trying to give somebody directions and they're starting here and need to end here. Well, there's more than one way to get there. In fact, there's lots of ways to get there. The straight shot is the white arrow. That's how you would go if you wanted to get straight there. But if this is like in a city, there might be buildings in the way. So you have to give them directions along the streets to get there, which would probably mean going east for a while, then north for a while. Component vectors are those directions, the ones that take you around the building. The thing about components is they have to be at a right angle to each other, which is going to introduce right triangles, which is why I need you to know your trig. So when we deal with component vectors, what we're dealing with specifically are two vectors that are broken up into the horizontal direction and the vertical direction. One of them is going to be acted on by gravity, and one of them is going to remain constant. You have to use your trig to figure this out. Now, for those of you who don't remember your trig and haven't been practicing, let's just for a moment be reminded about SOHCAHTOA just for a second. First, the 30 degrees is my angle of interest. It's my focus. So looking at that as my focus, the opposite side is over here and the adjacent side is over here. The diagonal is always the hypotenuse. So looking to SOHCAHTOA, sine of my angle is always going to be opposite over hypotenuse. And for this specific example, the sine of the angle is going to be V I over V, which ultimately means that VI is always going to be V sine theta. For projectiles, if you don't want to memorize, if you don't want to do the trig, you can memorize this because it will always be this for projectiles. We're going to have other stuff that won't be like that, but for projectiles, you can do this. And continuing with SOHCAHTOA, cosine of theta is the adjacent over the hypotenuse. For this, that's going to be cosine theta is Vx over V. So for this particular one, Vx is always going to be V cosine theta. Again, if you don't want to do the trig every time, you can memorize that. You just put it in a chart. It's always going to be there. All right, now we have to populate our chart, but we don't want to populate it with the 90 and the 30 degrees. We want to figure out the components of the object's motion. So starting with VI, V sine theta is going to be 90 times the sine of 30 degrees, which is 45 meters per second. Now this part I'm going to use your help on. The horizontal is going to be 90 cosine 30 degrees. And although I know that cosine 30 is 0.866, I don't know what 90 times 0.866 is. So I'll need you guys for that. I'm thinking it's probably 80 something, but I don't know.
90 times what?
0.866 for cosine of 30 degrees.
77.9.
That was close. 77.9 meters per second. All right. So, type 2 problems are characterized by now you having to figure out the components of the vectors. That's going to make this harder. It's going to add a step. All right. However, once you have those components, the problem becomes exactly the same as it was before. My job is to figure out the time, find out how long it's in the air. It's going to go up and back down, and then use that time to figure out how far sideways it goes. Again, the problem will be the same. So let's take a moment and do the algebra for this. So get rid of the trig here, so it's just in the way. And we will have, I'm going to go ahead and make upwards negative, just to screw with you a little bit. And to the right, I'm going to make positive. Understand, by making upwards negative, I'm making the 45 negative. Right? Because it's launched upwards. And I'm making the 10 positive. Now, if I just made downwards negative, it just would reverse those two signs. It will give us the same answer. Just want you to be clear, you pick it. And as long as you stay consistent, your answers are fine. It's when you don't think about it that your answers work out bad. Yeah?
Where did you get 45 from?
90 sine 30 degrees. Because sine of 30 is a half, right? All right, so I'm going to drop everything in here. I'm going to get 0 equals 1/2 times 10 t squared plus, oops, actually minus 45 t. Now you need to figure out time. Not too hard, because this is really going to be 5t squared minus 45t. And I know you have a compulsion to just divide by t, or something like that. Maybe move the 45t to the other side. Don't do that. Factor. Please, factor. You really are supposed to, because there's actually two times. There's t equals 0, and there's 5t equals 45. Which means t equals 9 seconds. But there's two answers for time. There's 0, and there's 9 seconds. Yeah?
Why didn't you take out 5 with 45? 5t. Then you could have made it t minus 9.
I just didn't. I could have. And you're right, I probably should have just factored it out. Now the reason we get 2 times is obvious. We asked the math, when is the ball on the ground? And isn't the ball on the ground 2 times? Right before you kick it and then after it hits the ground? Be aware of why we get 2 answers. It's usually helpful to know. Now I have to choose which time. I'm going to choose the 9 seconds. That makes the most sense. And then to find the range, I'm going to have to multiply 77.9 times 9 seconds. So, I don't know, 700 meters? Practice. It's 9. 9 gets close to 10. So I just did a little less than 10. All right. Hard problem? Does it seem okay? Variations. The first variation is to figure out how high it goes. They're going to ask that question. That shows up. Figuring out how high it goes means remembering that its maximum height is when the final velocity is 0. That's a variation. The other thing to think about with a variation like that is they might ask, where is the object when it's at its maximum height? So you would have to find out t. You'd have to find out t when the velocity is 0. It's not that hard. You just throw this away and start with the final velocity being 0 instead. But that will tell you how high it is at its maximum height. The more important thing you need to know actually has nothing to do with calculations at all. They're going to ask some qualitative questions about projectiles, and they use this one for their questions. And if you don't know what I mean by qualitative, they're going to ask you some things about the nature of a projectile. And often they'll use the type 2 for that question. So think for a moment about the path, the trajectory of a projectile. The ball we were just talking about will be located everywhere along this path at some time or another. The first thing you have to remember is that the horizontal velocity stays the same the whole time. So when I'm considering the horizontal velocity and drawing these in there, trying to draw them in so they're all the exact same size, pointed in the same direction, and they're all the same length. Because the horizontal velocity remained the same. And the problem we just did, that was 77.8 or 0.9 meters per second. And it stayed that way all the way to the ground. Which means the object is never stopped. At its maximum height, the y velocity is 0. At the maximum height, at this point right here. But it's not stopped. It does have its lowest speed at the top. That's important. That the object's lowest speed is when it reaches its highest point. It's never stopped, but it only has a horizontal velocity at the top. That knowledge is important and something that you need to know. Also, you need to remember that gravity is never 0. When it reaches its highest point, it's still being acted on by gravity. In fact, gravity is acting downwards on the object all the time in the same amount, 10 meters per second squared. We tend to forget that gravity acts the same way in this case as every other case. So when it reaches its maximum height, its horizontal velocity still is the same, its vertical velocity is 0, but it's still accelerating at 10 meters per second squared. The path of a projectile. Remember, the path of a projectile is called the trajectory. All right. We've done a type 1, done a type 2. We've explored the variations. However, there's type 3. Now, type 3 problems are arguably going to be the hardest of these. And they're not hard because the physics is any different. The physics is exactly the same. They're hard because they invariably will have a quadratic that has to be solved. And that makes students a little bit, concerned. And you should be, rightfully so, because it's a problem that is overly complicated with no real benefits. Physics-wise, the problem's exactly the same. I gain nothing about your physics knowledge by asking this question versus a simpler version. So understand that I don't think this is the kind of question you have to worry about. How fast was the car going, or was the object going in the first problem we did? Was it 5? It was 5, right? So I just want to redo that problem again. 10-meter tall building. This time we have a ramp, so the object is going to be projected at an angle. It's going to go farther because it's going to spend more time in the air. This problem brings together all the pieces now. You could be asked about the maximum height. You could be asked how far it goes. But ultimately, what really stinks about these problems is that they are overly complicated. We start looking at all the pieces again, and there are a lot of pieces. Delta y is going to be 10 meters. It lands on the ground, below where we started. The initial velocity, that's going to be 5 sine 30 degrees. The acceleration, 10 meters per second squared. The horizontal velocity, 5 cosine 30 degrees. Please notice I'm not drawing a triangle and drawing in the components. I don't have to. The vertical component is going to be sine. The horizontal component is going to be cosine. It's going to be the same as before. I could draw it out and everything. I just don't want to. You can see why. The problem still resorts to getting how long it's in the air. If I choose upwards to be positive, then this will be negative and this will be positive. The hard part, and this is going to be negative, is when I use my relationship to figure out the time, I'm going to have a quadratic. I'm going to have negative 10 equals 1/2 times negative 10 t squared plus 2.5 times t. No matter what I do, I have a quadratic. There's no easy way around it. Now, be honest with me.